Okay, briefly now. A of t equals A integrates to give us this, which integrates to give us this. If v of 0 is v naught, x of 0 is x naught, we get well, we got our values for x naught and v naught, and here they are. I'm looking for them one above the other. This for the v of t, this for the x of t. We've seen this. Now, if we want to look at an interval from sometime ti to sometime tf without having to worry about the global function, and we often have problems where we need to do that, or where we solve them most efficiently just by concentrating our attention on the interval, we can do this, okay? For ti, our velocity is vi, and that's v of ti, ati plus v naught. For xi, our position is x of ti, our initial time. And we plug that in and we get this expression, and that's what we're going to call x sub I. And then we get vf similarly, and xf, although that's not what I wrote down, I wrote down vi again. And that's what we have, okay? Then what we want to do is we want to write down our expressions for delta v and delta x for these functions in terms of xi and ti and vi and all that stuff. And we did that, and when I wrote down the expression for delta x, of course I had 1/2 a delta t squared plus v naught delta t. That's wrong on many levels. The delta t squared really should have been tf squared minus ti squared. I was anticipating where I was going and didn't bother with the details of how I was going to get there. V naught delta t has the problem that v naught is these t equals 0 time, and that's not part of the information that we're using within this one time interval. But it's easy to get that. We can sketch it schematically. We've got a VI and a VF on a V versus T graph, TI and TF, and a straight line graph because we're assuming uniform acceleration. So the slope of that graph is our delta V over delta T, and of course our delta V is VF minus VI, right? And that's going to be the slope of this trapezoid, if you wish, that connects TI to T equals 0, and this altitude of this trapezoid here is going to be V naught. Now, the rise of this trapezoid as we go from here to here is we calculate the rise. The run is from Ti to 0, that's negative Ti. We multiply the run by the slope and we get the rise. Rise over run equals slope, so rise equals slope times run. That's just rise equals slope times run. So there's the rise, and here's what then V naught is. Vi plus the rise. And that's an expression that we're going to substitute for V naught. So we do that at the appropriate point. Okay? We rewrite what we wrote. Delta V is this, delta X is this. And that's just straightforward from the X of t function and the V of t function. Then, for V naught, we substitute this mess. Okay, so we get this. Got our delta t here. Now, how does this simplify to give us something we can actually use easily on a single interval? Well, it's going to simplify to this. But it's not trivial, and there's some algebra tricks in here that are worth paying attention to. So algebra doesn't get too bad in this course. It doesn't get much worse than this. So don't be paranoid about the level of algebra and the tricks you've got to know. But these are tricks that you really want to pick up. You'll use them. Okay. So what we do first is, well, we use a distributive law here, VI delta t there, and this expression times delta t here, except we note that TF minus TI is your delta t. So when we multiply delta t by this, we have a delta t in the denominator multiplied by delta t. That goes away, and we land up with ti times vf minus vi. Now that is ti times delta v if you wish, but I left it in this form for a while. Not for long, because in the next step, we observe that vf minus vi is what? It's your delta v. And what's your delta v? You get that in terms of your vi and vf. It's just, and your trapezoid, it's just a delta t. Okay? So we substitute a delta t for the vf minus vi, we get negative ti times a delta t. Then in the next step, could have done it earlier, would have had one less step to look at, but that's okay. We factor the tf squared minus ti squared into tf minus ti times tf plus ti. We've got our vi delta t, and we have this, so everything else is the same. But now we note that our tf minus ti is just a delta t, so we got an a delta t here. We still have the tf plus ti here, and everything else is still the same. So what do we do next? Well, I could have done this in 2 or 3 steps, but it was not. We have this and we have minus this, okay? So we're going to take this term and minus this term and factor out an a. So we have a times what? A times whatever's left here, which is the 1/2 delta t times tf plus ti, minus the delta t times ti. And I wrote that as ti delta t just because of the order I want the delta t in. And then still we have our vi delta t. Okay, so now what happens? Well, both of these terms have delta t's on them, so we factor out the delta t. Okay, now we'll keep the 1/2 with the tf plus ti, then we have a minus ti. We put this over a common denominator. We have tf plus ti over 2 minus 2ti over 2. So it's tf plus ti minus 2ti, which is tf minus ti over 2. And now tf minus ti is another delta t, isn't it? So now we have a delta t and a delta t, so we have a delta t squared. And then we have the 2 in the denominator, which we haven't done anything with. Well, we'll bring that out as a 1/2. And here we have this, which is the advertised expression that we declared at the end of a lot of bad algebra in class. Careless algebra. Some of it bad, mostly careless. Okay, so we have this equation. We also have this equation. Okay. And this equation just rearranges to this one in the obvious manner. Now, if we eliminate delta t between the 2 equations, we solve this one for delta t, plug in for the delta t here, and do some rearrangement. And that takes a little bit of algebra, kind of similar to some of the steps we did here. But if we do that, we end up with this equation. And if we eliminate vf, which is easy, you have this expression for vf. I think I said that before too. We don't want to eliminate vf, we want to eliminate a. So we have an expression for a here. Solve this for a, plug in, and plug that in here, and simplify it, and we end up with this. And that algebra is relatively easy. Okay, so that's how we get these equations, and these equations have a really important property, in that if you know any 3 of the terms, v naught, vf, delta x, delta ta, on an interval, then one of these equations will have those 3 terms, plus another one that you can solve for. So that's really kind of powerful and really neat, and it's really kind of a synthesis of uniformly accelerated motion.